4. Early detection of X-propagation in power-aware simulation verification using UPF IEEE 1801. Abstract. So one of the goals of power-aware simulation verification is to detect X-propagation and isolation violations in the design. The current method devices to mitigate these issues largely depend on the scoreboard and to detect the integrity failures caused by the X-propagation. In this traditional approach, a significant amount of time is necessary to trace the origin of the invalid X values using waveforms. Hence, the turnaround time for bug detection and validating the corresponding bug fix is high for the power-aware simulation. The proposed automation approaches automatically translate the power design into checker and assertions. The generated checkers are capable of detecting X-propagation and also isolation violation and are instantiated in a hierarchy parallel to the SOC design. These checkers will enable the verification engineers to pinpoint the origin of the invalid X values with a low turnaround time. This paper covers the details, the method, and generates assertions and checkers for power domains, signal isolation, state retention, and restoration, which essentially left shift the power-aware verification. The unexpected challenges in generating such automated assertions are addressed in this paper, and practical solutions are provided. Instruction. This paper facilitates verification engineers who write power-aware test benches at the SOC level. Despite its importance, the power design is often added at the later stages to the SOC because it is beyond the regular functional operation. The new release of the Wilson Research Group and Matter Functional Verification Study find that the third lead cause of the chip respin is due to the issues in the power design. This observation suggests the need for the completion of the power-aware verification with a shorter verification cycle. So, in an SOC design with multiple IPs, each IP can move between power modes, power off, power on, sleep, to reduce the leakage power. Depending on the power mode is on operation, the independently powered region of the IP, namely power domains, can be turned on and off as shown in the figure 1. During such power on-off situation, retention cells save and restore memories and register values before and after shutdown respectively. There are isolation cells that keep the turn of the IP outputs in a previously defined values. This is how the shutdown IP does not corrupt the other active IP functionality. Successful development of the low-power semiconductor design includes checking UPF description as well as verifying the UPF against the design at multiple stages in the project. The power management verification approach described in this paper verified the functionality of the power management element described above to address the challenges in the left shifting and the verification. Figure 1, SOC with power design. Figure 2, X-propagation and distribution. A. Problem statement. The low power design and verification, the debug challenges are complicated and resource and time consuming due to the complex power management architecture and the instrumentation implication in the actual design. Power-aware verification, which employs the UPF power describing the power intent, requires significant simulation time compared to the simulation without UPF. The power switches described in the UPF file control the power supply to the power domains based on the power modes. Since not all blocks are powered down during a UPF simulation, X-propagation can occur and poses challenges to root cause analysis (RCA) of the bugs for the origin of X-propagation. A single X value can propagate and get distributed to thousands of signals within a clock cycle shown in figure 2. And among those signals, many can have valid X values during the power down phase. But the rest of the signals are supposed to retain the binary values. Waveform analysis for RC is time consuming and it is necessary to leverage the automated approach. Tool-generated assertion or low-power checks are used widely in the low-power verification. However, they may not be exhaustive in all designs for following reasons. Specific design requirement to new set of protocol speeds now and then. C. Not all EDA vendors support both UPM and CPF-based automated assertion generation. The static checker provided by a major EDA company can cover the missing isolation cell, which checks the presence of the isolation cells in the input and output of the power domain. However, this strategy does not cover the operation of the control signals of the isolation and retention cells that need functional verification to ensure seamless switching between power modes, as shown in Figure 3. Figure 3, power sequence, ISO enable, retention enable, power off, power on, retention disable, ISO disable. Possible root cause of X-propagation bugs. X-propagation can occur for multiple reasons and it can categorize into 4. 1. Missing isolation cell, missing control signal, missing connection in the data signal, wrong power sequence control. This scenario must not be present in power-aware simulation to eliminate issues like X-propagation and other bugs. C. Proposed solution. To address the issues mentioned above, we propose an approach by generating automated checker before simulation to verify the power control sequencing in the SoC. The proposed approach will also enable the early detection of the design bugs independent of the simulator tool used. At the first, UPF and RTL files are compiled, and from elaboration log, the list of all UPF objects and the RTL signals connected to those UPF objects are extracted. A Python-based parser was developed to automate this process. Then the assertions are generated from a template and instantiated in the test bench via checker modules. The added advantage of the automated assertions is left shift of RCA. Unexpected X values in the signals will fail the corresponding assertions. This failure of automated assertions enabled the verification team to RCA the X propagation instantly. Unlike simple assertions provided by static checking tools, these automated assertions are aware of the SoC design and hierarchy, along with the SoC power control signals, which is the prime feature that enables easy detection of X propagation. This paper is organized as follows. Section 2, background and related work about the specification and verification of the power-aware designs are studied. Section 3 details the solution for generating automated checkers and assertions to verify the power control sequencing. The case study in the Section 4 describes our observations in a real SoC design. Finally, Section 4 summarizes our work and outlines the future work. The 2, background and related works. A. Unified power format. HDL independent power specification format is standardized by the electric design and automation EDA's industry because of its benefits, the early power aware design. Two familiar format of the specified power design was developed by the industry consortium. The common power format CPF and the unified power format UPF. The new IEEE 1801 standard extends the UPF. In this paper, we discussed the approach using the UPF standard. B. Power domains retention and isolation cell. The power management module is the one that controls the power up and power down sequences. It uses power switches to turn off the unused part of the design that needs to be isolated by power domain. The power domain can also contain retention cells. A register's power is turned off when its power domain or IP is turned off. Some registers also need to retain their values after being turned off. These are called retention registers, which restore their previous active values after being shut down. An isolation cell passes logic values during normal operation mode and clamps its output to some specified logic values when a control signal is asserted. It is required when the driving logic supply is switched off while the receiving logic supply is still on. C. Automated assertion generation from use cases. Traditionally, designers manually generate assertions according to their understanding of the design, which demands specialized knowledge. Even for experts, creating all required instantly manually can be time-consuming. This assertion can be grouped into two main categories, static and dynamic. We utilize the static extraction techniques, which we analyze the UPF description statically to derive the assertion. The UPF elaboration log is parsed and RTL hierarchical design signals in the UPF object are obtained, eliminating the need to check the validity of the generated assertions by design engineers or other techniques. The verification of the power design. In general, verification of the power design falls into three steps. First, it is verified that the design correctly entered the power state. Second, the SoC has provided correct signal transitions at each power state. Third, it is ensured that the logic behaves correctly when the SoC enters a power state. For example, the unit has no activity when powered down. Figure 4. Traditional approach for verifying power design. The many functional defects can be exposed to by simulating power design. The most important among them are incorrect switching of the power switches for power domains, falsely timed power state transition, wrong power states, and improper save and restore sequences for intention. Moreover, inadequate isolation problems resetting the block to an operating state when the power is restored. Incorrect level in shifting between the domains can be detected. The traditional approach to verify the X-propagation is to simulate the functional verification test cases and check if any of the scoreboard for data integrity checking is failing. The traditional approach adds the delay in detecting bugs in Power OS simulation. It is because the maturities of the design to support the data integrity will be available at a later point of time in the development cycle. As shown in Figure 4, it also adds additional overhead to the root cause of the bugs. On average, lint, compilation, elaboration with a UPF takes a day, and then the Senate simulation for 2 days, and a regulation simulation takes 5 days. After the regulation, the triage takes 5 days in case multiple failures are detected, and finally, fixing the design, the UPF files takes 2 days. Exact timelines per bug were not tracked during the original project. Hence, we estimated an average of 5 days of the triage after each regression. The related works and the paper confidentially sign off any low-power designs without consequences. Multiple low-power design issues and debugging strategies are discussed. The paper states with verification tools dynamic checking capability combined with the usual custom low power assertions, one is ensure that all the low power checks are built into the design and simulation run. The solutions proposed in this paper are a combination of the two dynamic checks and the custom LP checks. Our paper extended this approach by automating the generation of custom LP checks, reducing the necessity of the manual intervention and enabling scaling at the SoC level. The solution. To address the issues mentioned above, we produced a novel approach by generating automated checkers before the simulation to verify the power control sequence of the SoC. This approach comprises 3 stages. In the first stage, RTL and the UPF files are compiled and elaborated. The resulting elaboration log contains the list of all UPF objects and RT signals connected to those UPF objects. The second stage of the elaboration of log and UPF files are passed through the Python-based text parser to extract relevant information related to the isolation and retention strategies. The parser generate an intermediate file that are contained in the extracted data, which is necessary for the next stage. And third and final stage, the final Python checker uses this intermediate file to generate a checker and assertions to meet the power sequence shown in figure 3. Python is applied to the automated stage mentioned above. The generated assertions are instantiated at test benches via checker modules as shown in figure 11. Covers mean are included in the checkers to track checkers coverage. Extended UPF verification environment by adding automated assertion. The Python-based text parser is invoked from the make file after the compilation and elaboration is succeeded. The generated assertion checkers are verifying that for control and the sequencing written in the SystemVerilog. During the simulation, the verification environment applies the test cases to the test benches. It invoked a behavior corresponding to the functionality described in power intent. Once the checker coverage meets the target coverage, the power, control, and sequencing is verified. Figure 5. Automated generation checkers with assertions in Python. The first stage, preparation of the automation. One of the challenges in the creating assertion is UP files alone is insufficient. Is to gather the RT hierarchy information. An elaboration log is a readily available source to gather details of the RTL hierarchy because the RTL files are compiled, elaborated along with the UPF file. In our case, we use Cadence ToolFlow, and the elaboration is generated by the Xcelium. We can also consider developing a script to parse RTL instead of the parsing elaboration log, which is beyond the paper's scope. The second stage, the text parser and intermediate file generation. In the second stage, the elaboration file along with the UPF file is parsed to fetch the signal hierarchy that matches the power control sequencing as shown in figure 5. UPF index structure is parsed and evaluated in the information power domain is extracted as an intermediate file named design hierarchy list file DHLF. Information about the supplied state for the power domain, isolation for inactive domains, memory retention, and RTL hierarchy is gathered. The following is the example of the UPF elements that are parsed by the Python script. As shown in figure 6, the isolation cells can have many input elements such as domain, clamp values, isolation sense, etc. UPF file simplifies how to describe how the rules are applied in power domains as a whole. For example, the manner supplies 2 inputs can apply to all inputs instead of explicitly mentioning all individual ports. This rule can be overridden by the additional rules for specific ports. This syntax limits the parser to rely on the UPF file solely. So we have to use an elaboration log as stated before. The figure 6 defines the isolation set for power domain PD0, which with power supplied VDD_on and ground VSSI. The clamp values is defined by the minus clamp _value construct. These definitions are in line with the UPF standard. Applies to input to make the rule apply to all input in the power domain PD0 so that the elaboration log will help the parser with the list of all the signals. Figure 6 identified for installation. Figure 7 identifiers for retention memory. Figure 7 shows how retention cell is defined. The retention cell policy is set for power domain PD0. PD0 retention enable B is saved and restore signals with a sense low and high respectively. In figure 8, supply net VDD on and supply port AVD_TS are created per UPF construction. The figure 8 is the identifier for the power domains. Third stage, generation of assertions and checkers. In the third stage, the assertion checkers generated from the template verification environment is extended by the adding assertions and checkers. From the DHLF file, RTL hierarchy information is furnished into a checker template. As shown in figure 9, the generated checker will be compiled along with the necessary assertions that will be included in the test bench. To test the types of assertions generated and added to the checker, the first type of the assertion is for the basic power flow and the signals going outside the power domain, and the second type of the assertions are retention cell. So we have to do the types of checkers to verify the isolation cell. Check if the control the signals set toggled correctly in a power state. Sequences properties are used to capture this logic, and assertions are coded, which help us to check the operation of the SOC during the different power state. 2. Check if the signal is connected to the isolation strategy are clamped to the correct values. As mentioned in the UPF object, the RTL hierarchy signals for these assertions are obtained automatically using the Python parsers as discussed above. The figure 9 shows the power properties. The power gating is used to check the low power state entry and if the ISO is enabled. The assertion failed if the ISO enable is not set. The property is used to cover the property to facilitate the coverage. These cover properties help us to ensure that the all power domains are covered with entering a low power state. The sequence power gating sequence ISO check and property ISO check and are used to check the clamp value. These assertions will help us to detect the X-proper if the clamp value is improper. This will also help us to find the root cause of the functional failures during the low power simulations. Retention cells do not do the save and restore operation, and as stated earlier, so we need to check if all signals for save and restores are struggling during the power down and power up, respectively. Similar to the isolation checker, we have two categories of the checkers. 1. Save and restore the signals and toggling the appropriate data state, appropriate power state, that is during the power down and power up respectively. The signal connected to the retention cells should have the same value for before power down and before power down and after power up. This is achieved by using automated assertions. In figure 10, sequence power gating the sequence LT checkers and the property LT under retention check and are used to check if their value is retained during the sleep. As I mentioned earlier, the cover property is used to enable coverage for this retention check and will make sure that all retention cells are covered for low power entry. This assertion helps easy debug and find the root cause of the functional failure in the low power simulation. The figure 9 is temperature for the checker with assertions. Figure 10 is template for save and restore for retention cells. The figure 11 is assertion of a generated checker and assertion. Putting all together, the all parser will look out for UPF syntax. For example, set underscore isolation and RTL hierarchy paths are inferred from the elaborating log files. The assertions are then generated based on the template files. These assertions are grouped into a power, extension, and isolation for generating the full checker. Finally, the generated checkers are instantiated in the test bench as shown in figure 11. The added advantage of automated assertions is left shift of the RCA, root cause analysis. Unexpected X values in the signals will fail the corresponding assertions. This failure of the automated assertions enabled the verification team to RCA the X-propagation quickly, unlike a simple assertion provided by the static checking tools. Those automated assertions are aware of the SOC design hierarchy along with the SOC power control signals, which is the prime feature that enables easy detection of the X-propagation. The 4. Case study and the result. In this case study, a chip tape out with a 40 days starting from the sanity arc clean RTL to the beginning of the synthesis phase is used for analysis. And at the beginning of the project, it was not practical to predict the categories of issues we could encounter while the verification was progressing. It was also impossible to expect any of those issues could slow down the verification effort. Once the project commented, a few bugs were detected at the early stage, which belonged to the basic sanity. After the initial bug findings, the detection of the rest of the bugs were delayed despite continuous verification efforts by the verification team. This is due to the complexity of the root cause analysis and the associated long simulation cycles. This impact on the schedule can be observed in Figure 12, which shows the number of bugs accumulated over time. Here, most of the bugs were reported midway through the project timeline, and the bug trend was stabilized only toward the tape-out. Figure 12, project without automation module. The Figure 13, project with an automation module. To the left shift the verification cycles and avoid the delay that mentioned above the future project. The team evaluated all the bugs reported and the time taken for the RCA of each bug. Based on the analysis, the team concluded introduced and automated the checker and can accelerate the bugs in detection process and reduce the time necessary for RCA. The reusability of the checkers was also important, which could further reduce the effort essentially in upcoming project. Hence, the checkers were developed generally to ensure reusability. After the proposed automation approach was developed, and the same project was executed to observe the expected advantage. For proof of the concept, we evaluated time taken to find the same amount of bugs in real project. That is, 11 bugs after introducing the proposed methodology into the verification pipeline. The key observation in this exercise was that effort for root cause analysis had reduced significantly since the checker failure brought the attention of the RCA engineers closer to the root cause of the bug. As you observed in the Figure 13, the most number of the bugs were identified at the early stage of the verification. The bug trend is stabilized 9 days before the synthesis phase, which is approximately 20% shift left. The observed result met the expectation by introducing the automation into the verification pipeline. The Figure 14 shows the timeline for the traditional and automation approach, and the left shift achieved for reducing the verification cycle. It is also important to point out the simulation time necessary to find the same bug using the traditional approach and automation approaches is comparatively lesser. And the traditional approach, the simulation has to wait until the X value propagates until the SOC and reaches the scoreboard and of assertion to fail. On the contrary, the automation approaches, the assertions the checker will fail the moment the unexpected S value is found or the power sequence is violated. To implement the proposed approach, the effort necessary is approximated as follows. For the preparation of the scripts and checkers, 10% of the additional effort was required at the beginning of the project. However, 25% of the time saving was observed in triage phase since the checker helped to pinpoint the root cause. Since we prepared the proposed approach with reusability as a key factor, subsequent project has reduced the effort at the deployment stage. The 5. Conclusion. 1. Our contribution compromised the automatic generation of checkers and with assertions of cover points from the UPF design. The generated checkers compactly describe the functionality of the power control and sequencing. Simulating the power-aware scenarios, which include the generated checkers, will automatically verify the associated power and controlling sequence. The key benefit of this approach is high degree of the scalability, respectively of the number of the power domains presented, the design and reduced out of the need for manual invention for each of the assertion generated. Additionally, the assertion coverage enables metric-driven coverage, metric-driven verification for the verification sign-off. A shorter verification cycle for the power design lowers the risk of the late and costly redesign. The figure 14, the RCA left shift. And in this contribution, we are motivated by the needs for a left shift of verification effort by leveraging the automation approach to avoid the detection bugs while nearing the tape-out schedule. Without automated checkers, most bugs were reported midway through the project timeline, and the bug trend stabilized towards the tape-out. However, in the case of the automated checker, the most significant number of the bugs are identified at the early stage of the verification, and the bug trend stabilized much before the tape-out. The observation result met the expectation by introducing the automation into a verification process. A small investment in automation will significantly reduce the verification cycle and unnecessary design iteration during later phase of the design. Okay, thank you. There are also the 10 references, and thank you for your time. And this was automation DVCON paper, automation for early detection of X-propagation in power-aware simulation verification using UPF IEEE 1801. Thank you again. See you next time.